Hello, my name is Akashdeep. I would like to thank the organizers for the opportunity to speak. So I'll talk about the existence of multiple closed CMC hypersurfaces with small mean curvature. Throughout the talk, M n plus 1, comma G will denote a closed Riemannian manifold. And let us consider the space of closed hypersurfaces in M. On this space, we have the area functional. So given a hypersurface sigma in M, by area of sigma, we mean the n volume of sigma. And minimal hypersurfaces are precisely the critical point of the area functional. More precisely, let X be a vector field on N, and Fxt be the flow of X. Then we can consider ddt at 0, area of Fxt sigma for some hypersurface sigma. And this is equal to minus integral over sigma inner product H sigma comma X. So H sigma is the mean curvature vector of sigma. And sigma is called minimal. If and only if ddt at 0, area of Fxt sigma is equal to 0 for all x. And from this first variation formula, we can see that this is 0 if and only if the mean curvature vector of sigma is identically equal to 0. So sigma is minimal if and only if the mean curvature of sigma is identically equal to 0. More generally, one can consider two-sided hypersurfaces. The two-sided means that its normal bundle is trivial. So we can consider two-sided hypersurfaces with constant mean curvature. That is CMC. So for C greater than 0, let us consider the AC functional, which is defined on the space of regions in M with smooth boundary. So that omega be a region in M, then AC omega is equal to area boundary omega minus C times volume of omega. And as before, let X be a vector field on M and Fxt be the flow of X. Then we can consider ddt at 0, AC Fxt omega. The first term is area boundary omega, which is same as before, and we get minus integral boundary over integral over boundary omega, inner product, the mean curvature of boundary omega comma x. And for the second term, we have C times integral over boundary omega new boundary omega comma x. The new boundary omega is the unit normal along boundary omega pointing inside omega. So if we rearrange this, we get integral boundary omega minus mean curvature boundary omega plus C times new boundary omega comma x. Therefore, from this first variation formula, we can see that omega is a critical point of AC functional if and only if ddt at 0, AC fxt omega is 0 for all vector field x. And this happens if and only if the mean curvature vector of boundary omega is equal to C times new boundary omega. So this is same as saying that boundary omega is CCMC. So CCMC hypersurfaces are precisely the critical points of the AC functional. Now I would like to talk about the min-max construction of closed minimal hypersurfaces and closed CMC hypersurfaces. But before that, I'll briefly talk about the min-max method in the finite dimension. So let n be a smooth finite dimensional manifold, and f from n to r be a C2 function. Then the most straightforward way to produce the critical points of f is perhaps minimization. But using minimization, we can only capture the stable critical points of f. To capture the unstable critical points of f, we need min-max. So using min-max, we can capture the unstable critical points. So for this min-max method, let us fix x. Let's consider x, which is a finite simplicial complex. And let R be a homotopy class of maps so phi is a homotopy class of maps from x to n. Then the min-max number associated to the homotopy class phi is defined as follows. So we denote it by m phi. This is equal to sup f phi x. So f is the function on n, which we fixed at the beginning. We consider sup f phi x. X is in capital X. And then we take in over all phi in the homotopy class phi. So m phi is sup f phi x. Small x is in capital X. Capital X is the parameter space. And then we take in over all phi in the homotopy class phi. And then we have the following min-max theorem. So then there exists a point P in N such that P is the critical point of F, that is dFP is equal to 0 and F of P is equal to this min-max number M phi. This is the min-max theorem in finite dimension, and uh, here we assume that N is a finite dimensional manifold, but this theorem can be suitably extended in the infinite dimensional case, that is when N is an infinite dimensional Hilbert manifold. So I'll just illustrate this theorem by an example. So let us consider the torus. Let's consider a torus embedded in R3. We have the height function on this torus. So we consider the height function on this torus, and this point, which we call P naught. This point is the point where H attains its minimum. So P naught is a stable critical point of H, but H also has another critical point. So let us call this point by P. So P is an index one critical point of H. This is an unstable critical point. And P can be captured by a one parameter min-max as follows. So near P, the torus looks like this. This is the point P. And let us consider this curve. Let us call this curve by C. So C is a map from S1 to T. And let us say that phi is the homotopy class of C. Then from this picture, we can see that the height of P, that is HP, is equal to sup HCT. T is in S1. And for all gamma in the homotopy class phi, so let us say gamma is this curve. For any curve gamma in this homotopy class, we can see from this picture that there exists a point on this curve gamma whose height is more than the height of P, that is sup H gamma T. T is in S1 is greater than or equal to HP. Therefore, we can say that HP is inf of this sup, that is, so combining these two, we have HP is equal to inf of sup H gamma T. T is in S1. And then we take inf over all gamma and phi. And we can see that this quantity is the min-max number associated to the homotopy class phi. And this is equal to h of p, where p is an index 1 critical point of h. Okay, so this was min-max method in the finite dimensional setup. And we would like to use a similar min-max construction for closed minimal hypersurfaces and closed CMC hypersurfaces. But in that case, we have to use the min-max on infinite dimensional spaces. More precisely, we need to work with the following two spaces. So let us consider the space of Cacciopoli sets, which we denote by Cm. This is the space of all regions in M. That's the region U subset of M such that the, the perimeter of U is finite. I'll explain this. And Zn M comma Z mod 2. So these are called the space of n-dimensional flat cycles in M with Z mod 2 coefficients, but this can be thought of roughly as the space of closed unoriented hypersurfaces sigma which bound a region. So sigma was the boundary of U, where U is a Cacciopoli set. So U is in Cm. So we say that E is a Cacciopoli set, that is E belongs to Cm if and only if E is Hn plus 1 measurable. So Hn plus 1 is n plus 1 dimensional Hausdorff measure, and this is almost same as Borel measurable. So E is measurable, and the distributional derivative grad chi E. So chi E is the characteristic function of E. E is a radon measure. So this is the definition for a Cacciopoli set. This is what we mean when we say that E is in Cm. And if E is in Cm, we can talk about the boundary of E and the unit normal nu E along boundary of E, which points inside. This is inward pointing unit normal on boundary. We can talk about the boundary E and nu E in a measure theoretic sense. And this boundary E will not be C1, but it is n-rectifiable. We have boundary E and nu E such that we have the following equality. So integral over E divergence x dHn plus 1. So this is the n plus 1 dimensional Hausdorff measure. This is equal to integral over boundary E x comma nu E. So this is the n-dimensional Hausdorff measure. So this holds for all vector field x on M. And we can see that if E is an open set with C1 boundary, this is Stokes theorem. And we can think of the Cacciopoli sets, that is regions with finite perimeter, as some kind of generalization of open sets with C1 boundary.